Hello everyone, today we're going to be going over the 20s. So first of all, we're going to take care of a little bit of language that we're going to be using in this unit. One of the words you need to know is directly proportional or a direct relationship. A couple things you need to know about that is that if we're having it on a graph, we will go through 0, 0 on a graph. So that's kind of one of the key points. If you're wondering where to write this, right on the front side on the left-hand side, right below Pearl, you should be writing this information about a direct relationship or being directly proportional. They mean the same thing. Couple things that go along with that. Whatever one variable does, the other variable does the exact same thing. So if one variable triples, the other variable triples. Remember, you can pause this video at any point in time if I go too fast for you to write down things. An inversely proportional or inverse relationship, mathematically, if we look at a graph, these end up being a curve. And whatever happens to one variable, the opposite happens to the other variable. So an example would be if one variable doubles, the other variable is cut in half. So all this information that's here, really the stuff that you need to know about is the stuff in this very first column. We'll be using that all unit long. The stuff in the next two columns are just nice to knows. You'll get more of that in college. So if we look at this first relationship, pressure and volume, they are opposites of each other. If you increase the external pressure under a trapped gas, the volume of that gas will go down. So let me give you an example of this one. And if you're in class, you would see more of them. So here I have a syringe that's open on this end. It easily goes back and forth. But if I plug this end and I squeeze on the syringe, the pressure, the external pressure goes up and the volume goes down. And if I release this, as the volume inside increases, the pressure is going down. It's pushing that down. So again, increase the pressure, volume goes down, decrease the pressure, and the volume goes up. That's on a trapped gas with my finger over the top of it. When you're in class, we'll give you more examples of that. So those two are opposite of each other, and this is an inverse relationship. So this is the only relationship, this one right here, that they are the opposites of each other. If you're in class, you would see the marshmallow and the pressure volume gun. So what that means is if pressure goes up, volume goes down. So P times V, you always end up getting the exact same number. And this ends up being a curve on a graph. So as pressure is going up, the volume goes down. So that's what you end up getting for information. The next relationship deals with volume and temperature. And I want you to think about a hot air balloon. So hot air balloons, they have a great big opening at the bottom of them. That's where the burner heats up the air inside. And actually on a hot air balloon at the very top of them as well, they have a little flap that they can let hot air out of the top of the balloon. So it's not like a traditional balloon that if you took a pin and you poked it, it would explode. Hot air balloons actually are open at both ends. So as the internal temperature of that gas goes up, those molecules move faster and faster and faster, and they take up more volume. So that is a direct relationship. So this is a direct relationship. One goes up, the other goes up. So in this one, if volume divided by temperature always ends up giving you a constant, and since it's a direct relationship, it always goes through 0, 0. This next one, I want you to think about any kind of trapped gas. Let's think of a basketball. If you have a basketball and it's sitting outside all winter long, the temperature on the gas went down. And if you went outside and you took that basketball and you hit it against the ground a couple times trying to dribble it, the pressure in that basketball is probably extremely low and it doesn't want to bounce. But on the other hand, if it's the middle of the summer and you left your basketball inside your car on a nice, bright, sunny day, as the temperature goes up, the pressure goes up. So probably if you took that ball and you hit it against the blacktop, it probably would bounce better than it's ever bounced ever before. So this is another direct relationship. And if we look at the math of it, pressure divided by temperature ends up giving us a constant. and then it's another one that goes through 0, 0. So as temperature goes up, the pressure goes up, and those two are a direct relationship. So of the three relationships, this is the only one that you have to remember is an inverse relationship. So let's go to the next slide. Oh, we're a little too far. This next slide, this is just a little note at the top. This stuff you absolutely need to know, everything in that column. These next two columns, we'll talk about that probably more in college or if you take AP, but right now it's not going to be very useful to us in class. All right, so this graph over here, is this a direct relationship? The answer is no, because it doesn't go through 0, 0. Is this a direct relationship? Well, it goes through here, but that's not 0, 0, so that's not a direct relationship. This one does, in fact, go through 0, 0, and it is a straight line, so it is, in fact, a direct relationship. All right, so these steps are found right below where we just got done working. It says we need to convert all of our temperatures to Kelvin temperatures. Here's the formula for it. You might want to write that on your cover. We're going to be using this formula a lot in this unit. Step 2 says we're going to fill in the data table, and at some point in time, these data tables will disappear. You're going to have to decide if you want to keep doing them at that point in time. Step 3, it says look at your variable, whether it be pressure, volume, temperature, or moles, and find the variable that only has one piece of data. Start your problem with that one piece of data. 4, place a multiplication sign and division bar between each piece of data from step 3. I'll show you what that means in a little bit. Step 5, pick any variable that has a particular partner and write its label on top and on the bottom of the division bar. I'll talk about that as we're going along. 6, show how the variable changes in the problem and how it changes the other variable. Below the factor, show how the variable changes and assign the up and down arrows. This is not optional. And 7, depending on the problem, you may have to add another multiplication sign or division bar. Possibly repeat steps 5 through 8. Would it make it any better if I told you guys did this in 9th grade science? You did these almost exact same problems and you had no issue. So let's go through them and I'll show you what all those steps mean. So we have a problem. It says you place a balloon that's got 3,552 milliliters of air into it. You place it into the freezer. Think about that. Have you ever had a balloon from a party and it got cold? What happens to the volume of the air in it? You ever have a balloon from a party and it gets by the window or by a heat vent or it gets really warm? What happens to the volume about that? Think about that as we're going along. It says, will the volume of the balloon increase, decrease, or stay the same in the freezer? So we're going to do some math to figure this out. So we got 3,552 milliliters of air. Right here it says volume in our data table, so that is what we are starting with, 3,552 milliliters of air. And quite honestly, we don't know the final volume of air. That's what we're going to try to find out. It does say the balloon is at room temperature, which is this. And our first step from the front side said we cannot use Celsius temperatures. We must convert them all to Kelvin. So Kelvin equals 273.15 plus our Celsius temperature, so 22.22 degrees Celsius. So our Kelvin temperature in this instance ends up adding up to 295.37 Kelvin. So that's our initial temperature. So 295.37 Kelvin. And so I'm going to put a simple line through that, write that up here, 295.37 Kelvin. The nice thing about the Kelvin scale is that it has no negative temperatures. So that really works well with our kinds of problems, and that's why we have to use the Kelvin scale. So we did that. The other temperature that they give us is this negative 10.5 degrees Celsius. So in the freezer, it's negative 10.5 degrees Celsius. So we're going to use the same mathematical setup, 273.15, but this time we're going to go plus negative 10.5. And your calculators can handle that if you have a hard time doing that on your own. You plug that into your calculator and you follow the sig fig rules for addition and you get 262.7 Kelvin. And you write that into your data table. 262.7 Kelvin. And in this problem, we are going from 295 to 262. So our temperature is going down. On the first page, we said if temperature goes down, what should volume do? Well, it's a direct relationship. So volume should go down. So we would expect our answer right here to be smaller than the 352 or 3,552 that we started with. So by doing that information and thinking a little bit ahead of time, you can see if your answer actually makes some sense. So here we go, following the instructions from the front page. You start with what you're given. So you are given 3,552 milliliters. You put a multiplication sign, you put a division bar. These two are the variables that are changing. So I put K, I put K. And at the end, these two K's will cancel out, and I'll be left with my answer in milliliters at the very end. So now I go under here, and I'm going from 295.37 K to 262.7 K. My temperature is going down. So my volume should go down because they do the exact same thing. So how do I arrange these two numbers that when I do the math, I end up getting a smaller answer over here? So if you want your answer, this is my answer, to get smaller, you put the smaller of the two numbers on top. Want your answer to get bigger at the end, you put the bigger of the two numbers on top. So if we look at this 262.7 divided by 295.3, that's going to give us a number less than 1. And when you take a number less than 1 multiplied by this, you should get a smaller number. If I flip the 2 and I put the 295 on top and divide it by 262, that's going to give me a number bigger than 1, and therefore I should get an answer that's bigger than what I started with. So again, this part is needed, this part is needed. The K's cancel out, and when you do the math on all of this and you follow the sig fig rules, you get 3,159 milliliters, which is in fact smaller than what we started with, and the balloon would get smaller when you put it in the freezer. This is the prettier version of what I just did. Pause the video if you need to do so. You can see how I did the Kelvin temperatures right here. You're always going to get points for filling out the table when there's a table. Again, the K's cancel out and you're left with your answer in milliliters. This is all the work that you need to show. So there's going to be a point for this step, a point for this step, and a point for this step as you are solving the problems. This next problem is just doing the same problem, except for this time you're going to do it with Celsius temperatures, which we will never do in the problems, but we're showing you why you should never use Celsius temperatures in the problem. So I start with the 3,552 milliliters. I use the Celsius temperature. I did all the same work. And at the end, I end up getting an answer of negative 1,680 milliliters. Can you have a negative volume? Can you have a volume less than 0? The answer is no, and that's why we use the Kelvin temperature. So you always need to convert Celsius temperatures to Kelvin temperatures. All right, so here we go. We're going to do problem number 3 on your sheet at this point in time. So problem number 3 on your sheet. So it says you tie a rock to a balloon full of air, you throw it into a lake. Will the volume increase, decrease, or stay the same in the lake? And that's what we're going to find out. So let's look for the piece of information that's all by itself. We got 3.55 liters. So that's our volume, 3.55 liters. That's our initial volume. We got a temperature that's 21 degrees Celsius. So we'll get rid of that real quick. So 273.15 plus 21.00 degrees Celsius. That's what our Kelvin temperature is going to equal. So if we do that work, we get 294.15 Kelvin. And we write that into the problem. Put a simple line through it. Don't make it a big deal. 294.15 Kelvin, following the sig fig rules. So that is our initial temperature, 294.15 Kelvin. And the atmospheric pressure is 1.01 atmospheres. Now, a couple things that I have at the top. Millimeters of mercury pressure can be in inches of mercury, atmospheres, torrs, and psi. Don't let it throw you. Just make sure the labels are the same throughout the problem, and everything will work out just fine. So don't let pressure freak you out. All the problems work the exact same way. So that is our initial pressure, 1.01 atm atmospheres. Regular atmospheric pressure is right around 1 atmosphere. The balloon falls to the bottom of the lake where the temperature is 10.15. So I do the same math like I did over here, except for I use the 10.15. And when you do that math, you get 283.30 Kelvin. So that is my final temperature at the bottom of the lake. So 283.30 Kelvin. That is my final temperature. And I might as well circle it. My temperature is going from 294 to 283, so my temperature is in fact going down. Keep on reading, and the pressure at the bottom of the lake is 2.94. Makes sense that the pressure at the bottom of the lake would be greater than above the lake, so you got all that water pressing down on you as well. So 2.94 atmospheres. So my pressure is going from 1 atmosphere to 2.94, so my pressure is going up. And what is all that going to do to my volume? I don't know yet, so we're going to solve for this problem. So I'm going to raise everything up a little bit, do a little erasing. Again, feel free to pause the video at any point in time and know that you did these problems back in 9th grade science. So I start the problem with a piece of data that doesn't have a partner. That's my volume. So I start with 3.55 liters, multiplication sign, division bar. Then I can go with pressure or I can go with temperature. It really does not make any difference whatsoever. So atmospheres, multiplication sign, division bar. And now I'll go Kelvin, and equals, and these two K's will cancel out, these two atmospheres will cancel out, and I'll be left with my answer in liters at the very end. So now I got to put in some information. I'm going to raise this up just a little bit more. I'm going to use just my data table. So in atmospheres, we're going from 1.01 atmospheres all the way up to 2.94 atmospheres. So that's one thing I need to always write. My pressure is going up. If pressure goes up, what happens to volume? Flip to the front side if you need to. Pressure and volume are opposites of each other, or they are inversely proportional, so our volume would go down. So I need to arrange these two numbers so my volume will go down in number. So 1.01 goes on top and 2.94 goes on the bottom. Remember what I said from the last problem. If you want your answer, or I said our variable to get smaller, you put the smaller of the two numbers on top. If you want your answer to get bigger, then you put your bigger of the two numbers on top. I go over to this next one. This one's temperature. I'm going from 294.15 and I am going to 283.30 Kelvin. So you need to put that part. In this one, my temperature is going down. So my volume, and again, flip to the front side if you need to. If temperature goes down, volume goes down. So I want my answer to get smaller, so I put the smaller of the two variables on top, 283.3 Kelvin, 30 Kelvin. goes there, and the 294.15 goes on the bottom. I crunch all of that information, and I end up getting 1.17 liters as my final answer with the correct sig figs. Remember, this has 3 sig figs, 3 sig figs, 3 sig figs, so that's why my answer has 3 sig figs. Again, pause the video, replay it, do what you got to do, and remember, this part can go right here, and this part can go right there. It makes no difference which one comes first. And there's a prettier version. Feel free to pause the video if you need to do so at all. Make sure that you are filling out the data table when data tables are available. Make sure you're doing this step. Make sure you're doing this step. Otherwise, you're going to be losing out on points. This is all to get you to understand how to set up the problems. In a little bit, we'll get rid of the data tables, and you'll have to make the decision if you're going to keep the data tables. So here's sample 4. And this is the last one that we are going to do together. Then you should be able to handle the next page without any issue. So in the next day, you'd be working through all these problems on your own using these as examples. So we have 44.0 liters. So 44.0 liters. We have that. We have 22 degrees Celsius helium. So I'm going to get rid of that. So again, Kelvin equals 273.15 plus 22 degrees Celsius. If you do that math and you follow the sig fig rules for addition, you end up getting 295 Kelvin. Since we don't go to the hundredths place with that digit, then our answer doesn't go to that far. So even though this one goes to the hundredths, but this one does not, so our answer cannot go to the hundredths. So I put a simple line through that. I am lacking a little bit of room, so I'm going to write it right there. So that's 295K. So that's what I'm starting out with. Temperature 295K. And it tells me my pressure is 222 millimeters of mercury. Don't let that weird label mess you up at all. So 222 millimeters of mercury. That's the formula for mercury. And that's because how high a column of mercury would go up in a barometer. That's how the pressure is measured. It says in this problem, we squish all of it to 11 liters. So our volume goes to 11.0 liters. And the pressure goes to 666 millimeters of mercury. And it wants to know what the final temperature is in Celsius, but we would first have to find it in Kelvin and convert it over. So you only convert it back to a Celsius temperature if it asks you to do it, and there's only very few problems that will actually do that too. So we start with the piece of data that doesn't have a partner, and we fill out our data table. Our pressure is going up. Our volume is going down, and we don't quite know what that's going to do to our temperature. So we start with the piece of data that doesn't have a partner. So 295K goes there, multiplication sign, division bar. The other two do, in fact, have partners. So one partner goes on top, 1 millimeters of mercury, and the other 1 millimeters of mercury. And at the end, these two will cancel each other out label-wise and leave us an answer in Kelvin. And we can set up the other one right away. This one's going to be liters and liters. Those will cancel out at the very end, and our answer will be left in Kelvin. So that's what we're going to be aiming for. And again, these two steps, they could be flipped back and forth. That would be fine. All right, so for the millimeters of mercury, we're going from 222 to 666 millimeters of mercury. So our pressure is going up. So our temperature should go, and you can look at the front of your sheet, and you can see that if pressure goes up, temperature goes up. So again, think of this as a basketball outside in the wintertime or in a hot car. So I need my temperature to go up, so I put the bigger number on top. If I want my answer to get bigger, I put the bigger of the two numbers on top. In the last two problems, We wanted our answer to get smaller, so we put the smaller of the two choices on the top. But we want our answer to get bigger, so we put the bigger number on top. We go over to liters. We are going from 44.0 liters over to 11.0 liters. So our volume is going down. If our volume goes down, our temperature should go down. Think of a hot air balloon that's not quite so hot anymore. It doesn't seem like it's blown up as much. So we want our temperature to get smaller, so we put the smaller of the two numbers on top. You crunch all of that information and you go to the correct number of sig figs, you get 221 K. But we want our answer in Celsius for this problem. So our Kelvin temperature equals 273.15 plus the Celsius temperature. So we have 221 K equals 273.15 plus the Celsius temperature. So if you remember how to do this kind of math, we would end up taking 221 K minus the 273.15, and that's going to equal our Celsius temperature. So when you do all of that work with the correct sig figs, you get negative 52 degrees Celsius. Again, you would only be doing this for problems where it asks you to do it. Well, folks, that was a lot of teaching there. Again, pause the video, do what you need to do to make sure you understand it. The next page, we're not going to be teaching you anything. We're just going to expect you to use this information and ask us for help as you need it. Have a good day.